This is Vanshaj Gupta. I'm from Kent State University. I'm joined here today by my co-author Jaydeep Patel, and we'll be presenting our paper uh, titled CovBERT: Enhancing Sentiment Analysis Accuracy in COVID-19 X Data Through a Customized BERT Model. So, to give you some context about why we decided to work on this problem, is that when the pandemic hit our world, we were made aware of the advantages of social media that we have. The social media discourse can be used to analyze the public sentiment during a global catastrophe, which would be very useful for policymakers and even researchers and people in the medical profession. So, when deciding to work on this problem, we were faced by two unique challenges, challenges unique to the COVID-19 pandemic. One is that to analyze the sentiment of the public, we need to analyze the text shared by the public on social media platforms. But the pandemic has some unique linguistic attached to it. Some terms came up after the pandemic became global. Some terms were not known to us in our day-to-day life. For example, coronavirus, and even words like vaccines were not very frequently used in places like Twitter or Instagram. And also, just knowing the meaning of these words is not enough because that would just constitute the expression of the public. To understand the sentiment, we need to put those words in context. So these were the challenges that we were posed with, and this is how we started to work on this problem. To give you a brief introduction about our algorithm or our customized BERT model, is that we designed CovBERT, which is a specialized adaptation of the BERT model and is designed specifically for COVID-19 discourse. By incorporating pandemic specific terms, it enhances the precision of sentiment analysis. We've also integrated geolocation data to capture the multidimensional nature of public sentiment across regions. Our findings show that CovBERT significantly outperforms the conventional BERT model in understanding and interpreting this complex, evolving language. Thank you, and we are very excited to share more about the capabilities of our model and our research findings. To continue, Jaydeep will explain you the data analysis process of our model.
Hello, I'm Jaydeep Patel, and I'm going to explain the first of all data analysis based on geolocation. In this section, we talk about data analysis for the geolocation part of the paper. The analysis starts with the geodata dataset having COVID-19 related tweets. The raw user location data undergoes a transforming using a comprehensive city database. Locations are mapped to corresponding countries, enhancing the data sets structure and providing a more meaningful geographical analysis. Also, we visualize the most active user location based on tweet count. This is followed by a refined analysis focusing on countries after featuring engineering offering a clear view of the geographical spread of the conversation on COVID-19. Second is data analysis sentimental. In this slide, we explore the sentimental analysis process detailing how the sentimental dataset is prepared and analyzed. The sentiment data dataset is subjected to pre-processing including text, cleaning, and encoding. The cleaning process involves removing emojis, hashtags, and links and filtering non-English content. Also, sentimental are then encoded numerical to allow computational analysis. The word cloud visualization was used to display the 50 most common words in the tweet, providing a visual representation of the prevailing themes and sentimental in the data. Label encoding was done to convert sentimental categories into numeric format. The data set was then split into training, validation, and test sets, ensuring a balanced representation of sentimental across the subset. Now I'm going to talk about methodology based on geolocation. Geolocation analysis. This section focuses on mapping and understanding the geographical spread of COVID-19 discussion on X. So data standardization. Given the diverse format of the location data, we standardize it into a uniform country format using the world cities dataset. Visualization of tweet countries by country. The post standardized we visualize tweet concentration globally.
Also, as a part of the geolocation analysis, we have prepared two animations. The first animation shows the global progression of confirmed COVID-19 cases, and we can see as the time progresses, the spread of COVID-19 also increases globally. Then we have correlated this with our data set to see a relation between the volume of tweets as the pandemic progressed. And we can see there is a direct correlation between the COVID-19 progression and the tweets made by the general public. As the COVID-19 increases, the pandemic increased, the COVID-19 related discourse on Twitter also increased, formerly Twitter, now X. After this, we moved on to the sentiment analysis, and I'll be talking about the methodology that we used. So this section details the methodology for sentiment analysis, and it is aimed at exploring the range of emotions in public discourse during the pandemic. The processing steps were pivotal for ensuring quality sentiment analysis. We created a well-defined pipeline to achieve this. To process the data, emojis were removed. We used regular expressions, um, including emoticons, symbols, and flags, to remove all the emojis from the text. Then text cleaning was done. This involved replacing new line characters, removing links and mentions, stripping non-ASCII characters. Hashtags were also removed, and we also removed the special characters. Next, we moved on to tokenization. Tokenization divided text into smaller units or tokens for the model to analyze and interpret each path's sentiment. Now, to give a brief overview of the BERT model, because that was the basis for our for customized CovBERT model. This section introduces the BERT model, which is the bidirectional encoder representations from transformers. It has some key features that are pivotal in this paper. First is that the BERT model uses bidirectional training, which means that the BERT interprets context from both sides of the token, unlike previous models, which are unidirectional. So the context of the word lies in all of its surrounding text. It's not just the word and the text preceding that particular text. So that is why we use the BERT model, because it uses the bidirectional training. It also uses the transformer architecture, which utilizes, which is effective in NLP tasks. The BERT model is pre-trained and pre-trained on a large corpus of text, and then we can fine-tune it based on a specific domain, like we did for COVID-19. The BERT model uses a word piece embeddings to manage unknown words through subword tokenization. For example, if there's a word like malfunction, which is not in the vocabulary of BERT, the BERT uses the word piece embeddings, which means it will divide the word into known words. For example, it will divide the word malfunction to mal and function and then try to understand its meaning. It's very impactful in NLP. But the standard BERT model has some limitations that we exploited, that we worked on to improve it and use it for COVID-19. So the main limitation of the standard BERT model that we focused on was its limited contextual flexibility. The BERT's pre-training on a historical corpus does not effectively capture the nuances and evolving terminology of recent events or specialized domains, such as those witnessed during the COVID-19 pandemic. And this is what we worked on in this paper. So to give you a brief overview of the CovBERT model, this section presents an overview of the CovBERT model, our custom adaptation of the pre-trained BERT model, fine-tuned for analyzing COVID-19 related tweets. So we have used a customized tokenizer. The CovBERT extends the BERT tokenizer by adding COVID-19 specific terms. This is crucial for the model to recognize and understand pandemic-related discussions, which may include new terminologies and jargon that weren't part of the original BERT training data. There are a few changes that we made in the base BERT architecture, which are as follows. We added a new dropout layer with a rate of 0.3 for regularization. This was done because we have focused the BERT model on COVID-19 pandemic discourse, which can make it susceptible to overfitting. Adding a dropout layer will prevent this overfitting from happening. We have also added a linear output layer for classifying sentiments into 4 categories, because the data that we were working with had data divided into 4 different sentiment categories. Before feeding the data into the model, CovBERT pre-processes the data from tweets. This involves removing emojis, applying lemmatization, which means reducing the words to their standard dictionary form, that is no past tense, no future tense. It's the simple verb form of the words. And we have filtered out all the special characters. Coming to the training process, CovBERT is trained using the Adam W optimizer, which is a variant of the Adam optimizer with a weight decay. This is also again focuses on preventing overfitting. Talking about the evaluation and results, over multiple epochs, CovBERT achieved a training accuracy of 78.64% and a validation accuracy of 99.96%, which is a substantial improvement from the standard BERT model. To set a baseline for the CovBERT model and its performance, we also used various machine learning models for the same sentiment analysis. These models were the naive-Bayes classifier, SVM, logistic regression, LSTM, and also the standard BERT model. Here we can see a sequence of how these models are performed in sentiment analysis. We can see that CovBERT has outperformed all the base models, all the existing models that could be used for sentiment analysis, showing high accuracy of our customized BERT model. Again, here this is a graph showing the accuracy metrics for all the models, and we can see CovBERT gives an accuracy of 78%, and the model just below CovBERT is the BERT model, which shows an accuracy of 72%. So CovBERT does show a significant improvement from the BERT model in identifying COVID-19 related discourse on social media platforms. So to summarize the paper and our findings, in conclusion, CovBERT represents a significant advancement in the realm of sentiment analysis, particularly in the context of the COVID-19 pandemic. CovBERT, our specialized adaptation of the BERT model, has demonstrated superior performance in analyzing COVID-19 related sentiments. It showcases enhanced accuracy and a nuanced understanding of sentiments, outperforming traditional methods. The model's success is attributed to its unique approach, which includes a pandemic-specific vocabulary and geolocation analysis. This combined approach makes CovBERT a really powerful tool in analyzing pandemics and helping the decision makers and the policy makers. So to talk about the future scope of the project, I would again invite Jaydeep to present.
I'm talk about the future works. Looking ahead, we have outlined several key areas for further development and enhancement of CoBERTs. First of all, enhancing performance metrics. Our goal is the future enhance the precision and F1 scores of CoBERT to ensure more comprehensive performance analysis. Second, language support and accessibility. We plan to expand language support, aiming to make CoBERT globally applicable, particularly in the relief of the public health monitoring. The next one is adaptation for various domains. Adapting CoBERT for other rapidly evolving domains is our agenda, focusing on its application for real-time decision making. The predictive analysis, exploring the potential of CoBERT in predictive analysis, particularly for tracking public health trend and detecting misinformation, is a significant future direction.
Yeah, so we have fine-tuned the BERT model for COVID-19, but the fine-tuning process in itself is not very specific to any domain. So it is very flexible and can be adapted to any domain potentially. And we also wish to incorporate a misinformation detection algorithm in the CovBERT, which would allow it to segregate false news, false information from actual true information. So this is all from our side. Thank you for your attention and engagement. We are open to any questions if you have. Thank you.
Yeah, thank you, Vanshaj. I would like to know if any questions from forum. Okay, hope there are no questions and it was a good presentation. Thank you once again for your presentation. Now we'll go to the next author, Ricardo D. Thijin, Aishwarya Batra, Pradhan Koch, Nazif Manzoor, and Hema McKenna from Minnesota State University, United States of America, and I'm sorry if my pronunciation is wrong, and entitled on reviewing fit and SID metrics on generative adversarial networks. Dr. Ricardo, are you there?
Yes, I am. Good. Hello.
Yeah, hello. Yep. You can share your screen and you can go ahead with your presentation.
Oh, it sounds good.
Yeah, your screen is visible.
Perfect. All right. Hello, everybody. I'm Ricardo, and I'm going to present you our paper reviewing FID and SID metrics on generative adversarial networks. Yeah, I'm Ricardo, and I'm from the Netherlands originally, but I'm now currently studying in the United States, 20 years old. And well, I'm currently doing my master's in data science. And yeah, I'm also an active TA and a researcher in the field of computer vision. And yeah, today I'm going to talk about how the metrics FID and SID function on a variety of GANs. I'll talk in a second about what GANs are, but first our objective. Yeah, so we're going to measure FID and SID metrics, which are two metrics to measure the performance of GANs on two separate image-to-image GANs. Those are pix-to-pix and cycloGAN, and we'll train those GANs on our custom data sets called facades, maps, and cityscapes. Eventually, we had the goal to see if a GAN performs better in a certain domain, so on a specific data set, and also how both metrics behave. But first, let's talk about GANs. Well, GANs were first introduced in the 2014 paper, Generative Adversarial Networks. And GANs use a concept of utilizing the game theory to generate basically new images from an already existing data set. It isn't or based on optimization, which other approaches before GANs were using, but instead it's using a discriminator and a generator neural networks, to basically generate and improve its own results. So a generator results a new image, and discriminator looks at if the image is fake or if it's real based on a test set. And if it's determines it's fake and it is fake, then the generator will have to improve to get better pictures, and the discriminator at the same time will improve as well. Eventually, this leads to a score as good as possible, and in the end, then we will get realistic newly generated data, which is almost identical to the original data sets, almost as identical even that like we as humans can't really see a difference. Yeah, GANs are used in multi-domains. Like I said, we can use it to generate new pictures, but we can also, for example, use it to create photo filters, like for example in Snapchat, when you can do a filter on your face, and data augmentation to create extra data if you don't have enough data in your data set. But we also can use it for anomaly detection, say for example, to detect cancer in pictures more easily. We also use it for text to image. It's the back algorithm for text to image. So if you type something and an image gets generated, like for example in the newly neural network Midjourney, and also image to image, which for example translates satellite images to maps images. And that's what we're going to talk about more today. Image to image GANs are a translator basically for pictures. So you have one picture, you want to translate it to a different type of picture. And there are 2 or 4 types of eye-to-eye GANs. First of all, there's supervised, where we have a data set that is paired up. So we have one data set that contains, for example, on the left satellite images, and we have one data set that's on the right contains all map images of the same picture, and they are paired up, so the model perfectly knows how to basically translate the satellite image to map image. We also have unsupervised GANs, in which no pictures are connected to each other. That normally happens because there aren't a lot of exactly the same pictures available, but you still want to transform pictures from one domain to the other. You'll need a lot more data for this type of GAN. Then we have semi-supervised, in which there are a couple of paired up data, but there's mostly still unsupervised data, but there's just enough for the GAN to learn what it needs to do. And then there's few shot data, which uses metadata in combination with a small data set of images. And well, this is all used for two goals. Domain adaptation, which basically transforms the style of an image to a different domain style. And you can see that here in the map data set, in which the style of the greenery in the houses is transformed to a new domain, which is the map. Or we can use GANs for style transfer, which changes the complete style. For example, you want to have a person, but the whole person identification or like eyes or like even the whole structure can change. All right. But there are a couple of downsides to eye-to-eye GANs. They're bound to be unstable, and they mostly also lack diversity. But since a couple of years, there are some metrics that can provide good insights into these unstable and lack of diversity metrics. These are the Fréchette inception distance, which is a quite popular one, and the signed inception distance, which has been announced last year. And they both use the inception distance between image data sets to feature, to see what the distribution is between those sets. And two data sets would be the generated data sets and the test data sets. So yeah, what's the inception distance? Well, to measure the inception distance, the FID and SID metric use the perception v3 algorithm from Google. And this basically creates feature maps from all the images in the data sets. And eventually, after creating feature maps for all images, they get put together into a feature vector. And this gets done for both image data sets, the generated data, and the original data, and then the distance between those two vectors the distance between the two feature distributions vectors are measured, and then the distance between the two is the inception distance, and that gets calculated through two separate ways, the FID and SID. So we have FID that uses this formula to calculate the distance between the two distributions. And it shows us the closer to 0 means that the distribution of the generated image is closer to the distribution of the ground truth. And so because of that, we want to have it as low as 0. And the range of the FID is 0 to infinity, so the FID can become as high as possible, but you want to have it as low as possible, just so the pictures get better, basically. Then we have SID. This is similar to FID. It measures high correlation to our own vision interpretation, just like FID, and also it uses the inception distance. But it also has the ability, instead of going from a range to 0 to infinity, it has a range of -infinity to infinity. So this metric also has the ability to question the ground truth images compared to generated images. At some point, generated images can become so good that they might be even more diverse or have a higher variation than the ground truth. In that case, you want to lower the diversity. So you need a minus. You need to go minus, just so to say that it's getting worse again. SID is part of the SpiderGAN algorithm, and we used also their code on the GitHub repository to measure our results. This is the formula. And also, again, when the score is close to 0, the Gaussian distribution of the two image featured data sets lay closer to each other. So if it's negative, you want to go up again. All right, then we're going to talk about the data that we used. First of all, we used the facades data set. This is a data set that's created by the Center for Machine Perception. And this is a paired data set that includes images of different facades, or also known as fronts of buildings around the world, paired to a segmentation of their unique characteristics. And some of the unique characteristics also include, for example, doors, windows, and pillars, like you can see on the left. And also each building has different backgrounds, and well, some might even include balconies or molding. So these are also included in how far as possible. Then we also have the maps data set, and this is created with the pix-to-pix again, while it was proposed. It's also a paired data set, and like I said earlier, it includes satellite images and map images of that exact same location. But compared to, for example, the facades, it might be a way bigger domain difference, even though, yeah, segmentation is still kind of close. It still uses a lot of colors, but maps might be a little bit more different. Then we have Cityscape, and this is available on the Berkeley AI Research Group website. And it's also a paired data set, and it includes images of frontal views of city. And this was, from our perspective, taken from a car. And yeah, it also has a semantic view of the same view to which it needs to transform to. Then we have our GANs, pix-to-pix. We use the PyTorch implementation. And this is the first pioneering high-quality GAN, one of its kind, and also inspired a lot of GANs that followed. It's very good at generating on small paired data sets, image data sets, but as soon as the image data sets gets bigger, you can see that the results are actually quite decreasing. It uses skip connections in the generator, which avoids to overtrain on specific image details. You want to have the image to be as general, or you want to have the GAN as general as possible, so the image gets more general without unnecessary details. It also lacks cycle consistency and style translation, which does mean that it does do domain adaptation, but yeah, it can transfer over or change styles. It also doesn't do consistency verification, so it doesn't check if it's consistent, and yeah. Then we also used CycleGAN. This does, compared to pix-to-pix, address the consistency verification, and it was inspired by pix-to-pix. It's the next more known GAN after pix-to-pix. No paired data is required for this one, actually, but it also does work with paired data, so that's why we used it for our paired data objective. It does introduce new loss functions, adversarial, and also includes two-cycle consistency losses. What it basically does is it can both generate images from the test or from the goal back to the input value, and it can also generate, of course, from the input to the goal, to the target. It can generate both ways, and so for that's why we need two-cycle consistency losses. Yeah, like I said, it has two mapping functions, and yeah, we used the cycle consistency code from GitHub. All right, so then we get two results. On the left, we have the results generated images from pix-to-pix, and on the right, we have the images generated on CycleGAN for facades after 1 epoch, and for CycleGun after 8 epochs, and for Pix2Pix after 100 epochs. Unfortunately, due to time constraints, we didn't have enough time to train 100 epochs on CycleGun, and 8 was the max we could go for. But for our objective to measure FID and SID, it's less irrelevant because you just want to see, okay, how well does it do between the metrics. So after 8 epochs, FID and SID on CycleGun, for example, both have a pretty high score, but they're better, or at least for FID is better after 1 epoch, but SID is a little worse after 1 epoch, which could mean that SID has or is more sensitive to bed diversity and also variability. It measures both diversity and variability, and FID only measures diversity. So it could mean that in the 8th epoch there was less variability, and that's why the score is higher compared to the 1st epoch. And also for Pix2Pix, you can see that Pix2Pix is starting to generate better and better and better images, and you can see that in both metrics. And also the same for CycleGun, Pix2Pix and cityscapes. After 100 epochs, Pix2Pix is able to make a pretty good image, while at the same time CycleGun is still kind of struggling after 8 epochs, which is expected. And these are the results for FID and SID on the cityscape dataset. And yeah, you can see again that for the CycleGun, SID is performing worse again after 8 epochs. And also you see this time in the Pix2Pix model that after 8 epochs, SID is slightly higher than after 1 epoch, which would probably mean that, again, the variability is a little worse after 8 epochs, but the probability is that SID and variability gets a lot higher after 100 epochs. Then we have the last data sets, just to verify the results, the maps data sets. And you can see again that Pix2Pix is performing well because it has 100 epochs. But if we are looking here, then you'll see, yeah, again, SID is a little lower this time, probably because it's easier, because the domain is more different this time, so it's more easier to pick up the variability and diversity, so the results can yeah, generate better results. All right, so these are all our results over the 3 data sets and over all epochs. And from this, we can conclude that the FID and SID are closely related to each other. If one goes down, the other normally goes down as well, and if one goes up, the other, we could say, goes up too, except for the few cases that I pointed out earlier. And yeah, we can also say, since SID is proposed last year, that is a feasible alternative to the well-known FID metric. However, SID is a better representation, we would say, on the distance between the ground truth and distribution, as it measures both diversity and variability. And yeah, that's also because it can go to a negative score. So because of that, it's also can weigh higher. That's also why their scores are a lot higher in the first epoch, especially. All right, and then I have some recommendations. We used relatively small data sets. For example, for SAS, it's only 606 images big, but maybe results will be different, probably will be different when you use bigger sizes data sets. I would also recommend some more research on the SID implementation. We saw that it had some great benefits to use as a loss function, but maybe we could even use it implemented in the discriminator, and just so it could also train on this metric. And I would also recommend just looking at different GANs or data sets, bigger data sets, different GANs, later developed GANs, like for example, MUnit, to see what it does on those GANs. And also, I would recommend looking if, for example, data sets with mixed domains, for example, if the facades and cityscapes data set would be mixed together, if that would be of any influence to the FID and SID. If it's mixed domains for only the train set, then the FID and SID should be high because of the high diversity in the distribution. But if it's also high in the train set, then it should be better. All right, and thank you for your attention.